Good morning, students. Myself, Dr. Ragasudha, is here to talk on microscopy. The fascinating world of microorganisms would have remained unknown had the microscope not have been invented. Roger Bacon in 1267 described a lens for the first time. However, his observations were not pursued immediately. Thereafter, in 1950, Hans and Jachurius Jensen constructed a crude type of operational microscope by placing two lenses together, which permitted them to see minute objects. In 1609, Galileo Galilei made the first simple microscope with a focusing device called oscillae and observed the water fleas through his microscope. In 1617 to 19, the first double lens microscope with a single convex objective and ocular appeared. The inventor was a physicist C. Drebel. This microscope was used to study the cells, plant and animal tissue and also the minute living organisms. Till then, the name microscope has not been given to this device. The name microscope was first proposed by Giovanni Faber in 1625. The credit of developing a compound microscope with multiple lenses goes to Robert Hooke in 1665 from England. It was only after 1670 that a cloth merchant of Delft, Holland, Antony von Leeuwenhoek in 1632 to 1723 started his hobby of making microscopes, and in 1674 he discovered the fascinating microbial world through his microscope. His microscope has given a magnification of around 50 to 300 times the original size of the object. Considerably, progress was made in improving the microscope in the 19th century. The introduction of oil immersion by Amici in 1869, substage condenser by Abe in 1872, apochromatic objectives with suitable eyepieces by Abe and Jess in 1886 were landmarks in the improvement of compound microscope. Here you can see the picture of microscope developed by Anton van Leeuwenhoek, and the objects or the organisms which he observed through his microscopes were given in the form of drawings like figure A, figure B, figure E, F and G. They are nothing but different structures of bacteria. Jernik in 1932 has developed a phase contrast microscope. Knoll and Ruska in 1932 transmission electron microscope. Coons in 1945 has developed a fluorescent microscope. Merton in 1947 has developed interference contrast microscope. In the picture we can see sizes of different living organisms starting from human beings to small atoms, and under unaided eye, with unaided eye we can see sizes between 100 micrometers to 10 meters, whereas light microscope we can see from 100 micrometers to 100 nanometers, while using electron microscope we can see zero point 0.1 nanometers, that is the size of the atom, from the size of the atom to 100 micrometers can be observed using an electron microscope. Before getting into the details of the microscope, we have to learn or understand what are lens and the bending of light. Light is refracted or bent when passing from one medium to another, that is from air to glass. which is known as refractive index. Refractive index is a measure of how greatly a substance slows the velocity of the light. Direction and magnitude of bending is determined by the refractive indexes of the two media forming the interface. There are 2 points in the lens, focal light rays at a specific place called focal point. Distance between center of the lens and the focal point is known as focal length. Strength of lens is related to the focal length. Shorter focal length, more magnification. Here we can see a lens through which light is being passed and it is forming a focal point represented by capital F, and the focal length is represented by small f. Now let us see what is a light microscope. Light microscopes are of many types like bright field microscope, dark field microscope, phase contrast microscope, fluorescent microscope. All these microscopes are of compound microscopes, which means image is formed by the action of more than two lenses. In simple microscope, only one lens is used, where in compound microscope, more than two lenses are being used. First, let us learn what is bright field microscope, which is the basic microscope of all types. It produces a dark image against a brighter background, has several objective lenses. Parafocal microscopes remain in focus when objects are changed. Total magnification is the product of the magnification of the ocular lenses and the objective lenses. It's a picture of a microscope representing different parts of the microscope. The first one is ocular eyepiece, followed by body, then nose piece. Nose piece consists of 4 objective lenses, followed by mechanical stage. Mechanical stage is followed by a substage condenser, then aperture diaphragm control, below that base with light source, then followed by field diaphragm lever, and the uh, bottommost is light intensity controller. On the other side we can see arm, coarse focus adjustment knob, fine focus adjustment knob. There are 2 knobs here, and here we can see stage adjustment knobs. Lenses. In lenses we need to know about eyepiece and objective lens. Eyepiece has different magnifications ranging from 5 to 20 times. It has field lens towards objective and eye lens towards the observer. Whereas objectives are generally with 3 different magnifications. Low power is 10x, high power is 40 to 45x, and oil immersion is at 100x. The focal length of these are 16 mm, 4 mm, 1.8 to 2 mm respectively. These objectives are mounted on a revolving nose piece for convenience. The eyepiece and objectives are fitted to the 2 ends of a hollow tube called the body tube. Other parts of the microscopes include adjustment knobs, then stage, mirror, substage diaphragm, and condensers. Adjustment knobs. In some microscopes, coarse and fine focusing adjustment knobs are provided in order to lower or raise the body tube with lenses for rendering image clear. This is done by rotating of the knobs. The coarse adjustment is meant to bring to the object into vision, whereas the fine adjustment is used for focusing finer details. The next part is stage. The object to be observed is kept on a glass slide and placed on the stage. It may have clips to keep the slide in desired position or a mechanical stage for horizontal movement of the object. In some microscopes, the stage may be raised or lowered with coarse and fine adjustment for focusing the object. The next part is mirror. Mirror reflects light which is transmitted through the object for observing it. The mirror has 2 planes, one concave and the other plane. When natural light is available, the plane mirror may be used for reflection of light because concave mirror would form window images. With artificial illumination, the concave mirror is necessary for higher magnifications, whereas for lower, the plane mirror may be used. The next part of the microscope is substage diaphragm. This is meant to control the amount of light transmitted to the object. Substage condensers consists of convex lens which concentrates and intensify the light reflected by the mirror. With objectives of magnifications exceeding 10x, the use of condensers becomes necessary for narrowing the core of transmitted light, which would fill the smaller aperture of the objective. The condensers usually employed are called Abe condensers, and these are used with plane mirrors. Next, moving on to magnification. Magnification is defined as a degree of enlargement of the image of an object provided by the microscope. It is the product of individual magnifying ability of ocular and objective lenses. Example, if the magnification of your ocular lens is 10x, objective lens is 40x, the specific magnification is of 400x. 10 into 40 is equal to 400x. There are certain factors which play an important role in magnification. The factors are optical tube length, focal length of the objective lens, and magnifying ability of the ocular. The total magnification of the object image can be calculated using a formula: length of the optical tube divided by focal length of the objective into magnification of ocular. The next important point in bright field microscope is resolution power. It's an ability of a lens to separate or distinguish small objects that are close together. Wavelength of light used is the major factor in resolution. Shorter wavelength gives greater resolutions. Human eye resolution power is 0.25 millimeters. Here we can see, in order to increase the resolution power, we have to decrease the wavelength of light, which can be achieved by adding oil to the glass slide, which is known as oil immersion. Here in the diagram we can see, in absence of oil, the wavelength is more, whereas in presence of light, the wavelength is less, which gives high resolution power. Factors of resolution power: they are wavelength of light, which is usually of a visible region 400 to 750 nanometers, numerical aperture of the objective. These are the two factors which influence the resolution power. Numerical aperture is defined as a property of lens that determines the quantity of light that can enter into it. It depends on refractive index, abbreviated as N, and angular aperture, abbreviated as F. Thus, the formula for numerical aperture is n sin f, while the formula for resolution power is wavelength of light divided by 2 into numerical aperture. Bright field microscope is used to study wet mounts, hanging drop methods, and staining methods. In the coming class, next class, we will learn about other types of light microscope. Thank you.